This is the GMAT 41. You are welcome to our chemistry class. In our class today, I'll be teaching you about isotopy and isotopes. These are two terms that are used sometimes a bit interchangeably, but they are not exactly the same thing. And so today, you are going to learn about them, isotopy and isotope. Now quickly, I want you to look at yourself, then think about maybe your brother or your sister. Now you'll agree with me that the two of you are not exactly the same in every way, even if the same parent gave birth to you. This helps us understand the idea of isotopy or isotopes. Let's think of an element now. In one of our previous classes, we defined atom as a part of an element which can exist alone and take part in chemical reaction. Now, we say that atom is part of an element. So we can take element as parents giving birth to atoms. Now, an element can have two or more atoms. Yes, it's possible. An element can have what? Two or more atoms. Just like maybe a parent giving birth to two or more children. But now these atoms somehow, in one way or the other, may not be exactly the same in their behavior. There may be differences in one thing there. Even if these atoms, they belong to the same element. Such occurrence is what we call isotopy. Such occurrence is what we call what? Isotopy. Now, these atoms which belong to the same element, but their properties are not completely the same or exactly, those atoms are known as isotopes. Can we now define isotopy just as we have on the board here? Isotopy is a phenomenon, is an occurrence whereby an element can have two or more atoms which have the same atomic number, but their mass number are different. So you see that, right? Isotopy is a phenomenon whereby an element can have two or more atoms. Now, these atoms, they have the same atomic number, but their mass numbers are different. I want you to take note of this word, phenomenon. Phenomenon. An occurrence. Are you following, right? Okay, now let us look at an example here. The element chlorine can exist in two forms as an atom. We have that which we call chlorine 35. You can see that here. That chlorine whose mass number is 35. The atomic number is 17. Then we have this called chlorine 37. You can see that the mass number of that chlorine atom is 37, atomic number is 17. So can you see the differences there? Their atomic numbers are the same, but look at their mass numbers, different. Even if these two atoms are atoms of the same element known as chlorine. We have other examples. We have that of neon, neon 20 and neon 22. We have carbon 12 and carbon 13. We also have the element copper having two atoms. That of copper 65 and copper 63 and copper 65. So the occurrence of an element having two or more atoms, that the atomic numbers are the same, but mass numbers are different. That phenomenon, that occurrence is what we refer to as isotopy. Now, what is responsible for the differences in their mass numbers? Because we say the atomic numbers are the same, and we know that atomic number is also equal to proton number. We've already studied that in our past classes, okay? Atomic number is the same as proton number. So if we say that isotopy is the occurrence or phenomenon whereby atoms of an element have the same atomic number but different mass number. What is responsible for their different mass number? Because their proton number will be the same, since the atomic number is also the same. The differences in the mass number is as a result of different neutron numbers. So as a result of what? Different neutron numbers. So this pair of isotopes we have here, chlorine 35, chlorine 37, the differences in their mass number is as a result of different neutron numbers, because their atomic number, which is also the same as their proton number, are the same. So don't forget that. Neutron number of isotopes are different. Okay, now let us quickly talk about isotopes. What are now these isotopes? We've talked about isotopy. Isotopes are those atoms. Isotopes are those atoms of the same element that have the same atomic number but different mass number. Did you take note of the point? Isotopes now are those atoms themselves. So isotopes are the atoms. Very important. One can quickly think about maybe the word pollution and pollutant. Pollution is the process where dangerous materials or unwanted materials or harmful materials are released into the environment. The process where you release these harmful materials into the environment. That is pollution. Then we now have pollutant. Pollutants are now those harmful materials, those unwanted materials that you release into the environment. So the same thing goes with isotopy and isotope. Why isotopy is the phenomenon, the occurrence. Isotopes are now those atoms that occur with different mass numbers but the same atomic number. Let us now talk about the scientists who first discovered isotopes. The name of the scientist is J.J. Thomson. J.J. Thomson. Please take note of the spelling of this Thomson. There is no P here. Take note of that. Thomson. Alright, now he discovered this in 1913. The year 1913. Okay? Sometimes we pronounce it as 1913. And he showed that the element neon can exist with two atoms having different masses. One of them of mass 20, the other of 22. How do we detect isotopes? Which instrument do we use to measure the mass to charge ratio, which can now help us to isolate these isotopes into their amount, into their relative abundance, that is their quantity in a given sample? We use the instrument known as mass spectrometer. You can also refer to it as mass spectrograph. This instrument ionizes the sample containing the isotope, alright, and then measure the mass to charge ratio. Now we're going to talk about the properties of isotopes and how we can use the knowledge of the relative abundance of the isotopes to calculate what we call the relative atomic mass. We have been able to define the term isotopy, and I've also explained what isotopes are. Now, I would like us to look at the properties of isotopes, and then how we can use the knowledge of isotopes to calculate the relative atomic mass, R.A.M, of an element. Here on the board, we have the properties of isotopes. I've written out some of them, and I would like us to look at these properties. Isotopes of an element have the same atomic number. That means that isotopes also have the same number of protons. So don't forget that. For example, chlorine 35 and chlorine 37, their atomic numbers are the same, 1717. Similarly, their proton numbers are also the same. So remember this, that isotopes, they have the same atomic number and the same proton number. Another property of isotopes is that their mass numbers are different. That we already mentioned when we defined isotopy. So isotopes have different mass number. You would recall when I told you what is responsible for the differences in the mass number. I told you is because the number of neutrons of isotopes are different. So saying that they have different mass number also goes to mean that their neutron number are also what? Different. Another property of isotopes, they have different physical properties. Don't forget that they have what? Different physical properties. This is because their mass number, alright, their mass number are different. Now, how does the mass number affect the physical property? Mass number actually determines the weight of an atom. And weight of something is a physical property of that thing. So if their mass numbers are different, it simply means that isotopes will have different physical property. So what do you think if you have the isotope of carbon, carbon 12 and carbon 13? Are their physical properties the same? No, they have different physical properties. Now I want to look at property number 4. That's the next one. Property number 4. Isotopes of an element have identical chemical property. They have what? Identical chemical property. Of course, we expect that because the number of protons and the number of electrons are the same for isotopes. You know that. Like in the case of chlorine now, for example, whether chlorine 35 or chlorine 37, they have 17 protons and 17 electrons, each of them. And that is why we expect their chemical properties to be identical. Let us now look at the formula we need to be able to calculate the relative atomic mass of an element from the knowledge of isotopes. On the board here, we have the two formula of interest. Okay, one of the formula is in terms of the percentage abundance. That is equation 1. Calculating relative atomic mass using the percentage abundance of the isotopes. And then the other formula, equation 2, is used to calculate relative atomic mass when the ratio of the isotopes are given to us in the question. So we have this R.A.M, relative atomic mass, is equal to summation. This sign is symbol of summation. AI times PI. What does this AI represent? I use it to represent the mass number of any of the isotopes. So if an element has 3 isotopes now, then this AI would be A1, A2, A3. That is mass number of isotope 1, mass number of isotope 2, and mass number of isotope 3. Then PI represents the percentage abundance or the relative abundance of each isotope in the sample. So again, if an element has 2 isotopes, then PI will represent the percentage abundance of isotope 1, can also represent the percentage abundance of isotope 2. Now in this equation 1, we are expected to divide everything by what? 100. You notice that here on this summation, under it I wrote I equal to 1. It simply means I represent any of the isotopes. So this means you add up the product, that is the multiplication of mass number by the percentage abundance. When you multiply them, then you add everything together. Starting with the first isotope down to any number of isotopes that you have in the question. Alright, take note of the denominator. When you are dealing with percentage abundance, then you divide by what? 100. In equation 2, relative atomic mass is equal to summation, the mass number times the ratio of the particular component. You add all of them together and then divide by summation, that is addition of all the ratios. We're going to see how we use this formula to calculate the relative atomic mass of an element. We are going to be solving this question where we are to determine the relative atomic mass of chlorine. So let us take a look at the question. Chlorine contains 2 isotopes with mass number 35 and 37 and percentage abundance 75% and 25% respectively. Calculate the R.A.M of chlorine. Alright, so how do we solve this problem? Let us bring out the things that we know as given in the question. Now we know the mass number of this chlorine, so I can just simply write we have chlorine 35, okay? Now this chlorine 35, we're given the mass number, so I will take that as A1. Are you following, right? Let this chlorine 35 be one of the isotope. So A1, the mass number of one of the isotope is 35. You can see the mass number here. Alright, if you read through the question, we're told that the percentage abundance is 75% and 25% respectively. That word respectively means the first percentage abundance belongs to the first mass number that was given to you in the question. So I would write P1, percentage abundance of the first isotope given there. That's 75%. 75%. There's something I want you to take note of here. The lower the mass number, the higher the percentage abundance. And the higher the percentage abundance of any isotope, the lower will its mass number be. Okay, now let us move on to the second one, chlorine 37. Chlorine 37, the mass number, that is the second isotope now, so we're going to have A2. The mass number is 37, you can see that. And then its percentage abundance, P2, is equal to 25%. Again, I want you to take note of this. If you add up the percentage abundances, alright, you are going to get 100. Please take note. Remember, from mathematics, we already learned that if you add up all percentages, you would get what? 100. 100%. Now, this question given to us, if you look at the information from the question, we know their mass numbers, the mass number of the isotopes, we know their percentage abundance. So, which formula will you use in solving it? Is it equation 1 or equation 2? Of course, it's going to be that equation that has percentage abundance, Pi. And that is equation 1 based on what I gave to you previously. Okay, so we are looking for R.A.M. We don't know. R.A.M. of chlorine. We don't know. R.A.M. of chlorine. Question mark. So I'll quickly write that you should recall. We have the formula that to calculate the relative atomic mass of any element, it is equal to summation of the mass number times the percentage abundance divided by 100. This is the formula. If I like, I can put I equal to 1 down to I. If I don't want, I might just forget about the I thing, okay? There is no error in that. Now, what does this summation mean? Watch now as I handle that. The relative atomic mass of chlorine will now be equal to this summation AIPI means you should multiply A by P. So if we come to the first isotope, the I will now be 1. Are you following, right? So this is going to be A1 times P1. A1 times P1. Since it is summation, we are adding. There is going to be plus A2, that is the second isotope now, times the percentage abundance of that second isotope, divided by what? 100. There are only two isotopes given here. So it's going to be A1, P1, A2, P2, you start. Then over 100. The R.A.M. of chlorine will now be equal to, let us now substitute. What's the value of A1? The mass number of the first isotope, which is 35. So it's going to be multiplied by its percentage abundance, which is 75. I will add this to the mass number of the second isotope. The mass number of the second isotope is 75, A2. I will multiply it by its percentage abundance, 25. Then all of this is to be divided by 100. I hope it's making sense, right? Do you have any challenge with this? Alright, that's good. I'm happy you are following. So you see the way I interpreted that formula. This summation AIPI, you can see clearly what that I represents. Isotope 1, isotope 2, isotope 3, isotope 4, depending on the number of isotopes given to you in the question. Now we're going to reach out for a calculator and see what this is going to give to us. So R.A.M. will be equal to 35 times 75. This gave me 2625. That is 2625. Then 75 times 25. 75 times 25. Something seems to be wrong there. Let's look at this. A2. Mass number of the second isotope. This is supposed to be 37. Okay, 37. I'm sorry for that error. That makes me a human, okay? That makes me a human. But I've corrected it. A2. Mass number 2 is 37. So we are multiplying it by P2, which is 25. Alright, A1 is 35, yes, and P1 is 75. So we are okay. Let's go. 37 times 25. 37 times 25 will give us 925. 925. So I'll be dividing this by 100. If you add up the numerator, this will give us 3,550. Again, I will divide it by 100. If you divide this by 100, you would get 35.5. Therefore, R.A.M of chlorine is equal to 35.5. And this is the answer. You could see why the mass number of chlorine, that element chlorine, if you see it written in textbook or you Google it, you would say that the relative atomic mass or the mass number of that chlorine is always 35.5. We shall take yet another question. When a problem is given to you on the relative atomic mass of an element such that the ratio of the isotopes of this element are given to you, how do you find the relative atomic mass of such element? Here on the board we have this question that we're going to solve to help us know how to handle such problem. Let us look at the question, please. Two isotopes of carbon are carbon 13 and carbon 12. The ratio of the isotopes in a sample were found to be 1:90 or 1:90. What is the relative atomic mass of carbon? So let us see how we solve this question. It's a simple one, not too different from what we did in the previous question. So here we have carbon 13. We have carbon 13. So the mass number A1 will be equal to 13. Now here they give us the ratio. Usually the first ratio will belong to the first isotope mentioned. So I'm going to write that the ratio of isotope 1, R1, is equal to 1. The next isotope is carbon 12. Carbon 12. So the mass number is 12. Alright, and then the ratio given, R2, is equal to 90. It's equal to 90. Now we are asked to find the relative atomic mass of carbon. We don't know. It's going to be question mark. So which formula do we need to solve this problem? Like I said, it depends on the information given to us here. If you look at this question, they give us the ratio of the isotopes in the given sample. And therefore, the formula we have to select is which one? That's correct. That formula that contains ratio. Let us do that and see. We're going to recall R.A.M of any element is equal to summation the mass number of a particular isotope times the ratio of that isotope. Because this problem is given to us in terms of ratio. We're going to divide it by sum. That is addition of all the ratios. You see, I've decided not to put I equal to this and that. I commit no crime. So let us move on. How many isotopes do we have here? Again, we have 2 of them. And so the R.A.M of carbon will now be equal to AI times Ri. So the first I will be 1 times R1, then A2 times R2. You add them together, that is summation. So that's going to be A1 times R1 plus A2 times R2. We're going to divide it by addition of the ratio, sum of the ratio. So it's going to be R1 plus R2. So let us substitute here and see what we're going to get. Mass number of the first isotope is 13, so we're going to multiply it by its ratio, which is 1, and then add this to the mass number of the second isotope, which is 12, times R2, the ratio of the second isotope, which is 90. All this will be divided by the summation of the ratios, which is 1 plus 90. So take a look. Okay, we have the formula. You know why we selected a formula to be this already instead of that of percentage abundance. We selected this because ratio was given to us in the question. And then this formula, I've explained that, the meaning on the board there. Okay, still similar with that of percentage abundance, only that we are now using ratio. The denominator is addition of the ratio. So we're going to solve out this and see what it's going to give to us. 13 times 1 is equal to 13. So this is equal to 13 plus 12 times 90, 1080. So this is going to be divided by 1 plus 90, which is 91. So this is equal to 1080, add 13 to it, you get 1093, that is 1093. We're going to divide this by 91. And therefore, the relative atomic mass of carbon will now be, if you divide this together, therefore the relative atomic mass, R.A.M, 10,093 divided by 91. This gave me 12.01. I can still approximate this to 12. Can approximate that to 12. And this is my answer. So you see, no wonder. If they ask you what's the relative atomic mass of carbon, whether you're reading your textbooks or you decide to Google it, you would always see it to be 12. An approximate value. Let us pick one more question and see how we can use the knowledge of isotope to solve some problems regarding R.A.M. When a problem is given to you and it is required that you determine the percentage abundance, that's the relative abundance, and the ratio, what do? I've got this interesting question on the board, so we're going to solve it and then we would learn how to handle such problem. Please, let us look at this question. If the average number of times the mass of one atom of copper is heavier than 1/12, the mass of carbon-12 is 63.5. Calculate I, the relative abundance of the isotopes, 65 copper and 63 copper. II, the ratio of the isotopes, 65 copper and 63 copper. Look at this long sentence here. If the average number of times the mass of one atom of copper is heavier than 1/12, the mass of carbon-12 is 63.5. That whole statement put together there is simply telling you that the relative atomic mass of copper is 63.5. How do we know that? Take your mind back to when I taught you about R.A.M. and R.M.M. That is relative atomic mass, relative molecular mass, even molar mass, the moles. Are you following, right? We define the relative atomic mass of an element as the number of times the average mass of one atom of that element is heavier than 1/12 the mass of carbon-12 isotope. So this definition, or this long statement here, is simply telling you that the relative atomic mass of copper is 63.5. So in some questions, they could just tell you the mean weight of so-so element. Are you following, right? The mean weight, the mean atomic mass. Once you hear average, mean, remember you are being given the relative atomic mass. Alright, now how do we determine the relative abundance of the isotopes? Let us see how we go about that. They didn't give us any relative abundance in the first part of the question, but before then, let's bring out what we know. From the question, we know the R.A.M. of copper. R.A.M. of copper given to us in the question is 63.5. Alright, now in the first part of the question, we are asked to find the relative abundance. So it's going to be the percentage abundance, abundance. Permit me to use this as percentage. Percentage abundance of 63 copper and 65 copper. I don't know. So I'm going to say let it be equal to question mark. So this is what we do. We're going to say, let me take 63 copper to be the first isotope and 65 copper to be the second isotope. Is that okay? So let P1 be equal to percentage abundance of 63 copper. 63 copper. So since we don't know it, we're going to say let it be X%. Is that okay? X%. I don't know it. Now there is something I told you earlier that if you add all percentages, you will get 100. Now look at this two marker. If the percentage of this marker is 30, then to get a percentage of this marker, it will be 100 minus this 30. You get 70. Does that make sense? So if I say, let P1 be equal to percentage abundance of copper 63, and I call it X. So it implies that P2 will be equal to percentage abundance of copper 65, and that will be equal to 100 minus X%. Because if you add up the two percentages, you should get 100. So this idea, this knowledge, we are going to use it and then substitute into the relative atomic mass formula. That one that makes use of percentage abundance. Okay, now let us write out the mass numbers given to us. A1, that is mass number of isotope 1. We've decided that isotope 1 should be copper 63. So the mass number is 63. And then isotope 2, the mass number is 65. So recall, recall that we know R.A.M of any element is equal to A1P1 plus A2P2 divided by A2 times P2, then divided by 100. There are just two isotopes here, so it's going to be 1 and 2. If I substitute, coming to this, relative atomic mass of copper given to us is 63.5, and that will be equal to A1 is 63 multiplied by P1, percentage abundance of copper 63, which is X. Then plus A2 is 65 times P2, percentage abundance of copper 65, 100 minus X. 100 minus X. We shall divide all these by 100. Now let's simplify this and see what we are going to get. From here, we have to cross multiply. We are solving for X now. Once I get the value of X, that will be equal to P1, the percentage abundance or relative abundance of copper 63. If I cross multiply, this times this will give us 6,350 equal to 63X, then plus, open up this bracket, 65 times 100 will give us 6,500. Then 65 times minus X will give us minus 65X. So let us collect like terms from here now. 6,350, this 6,500 will cross over. It's going to change, the plus will change to minus. Then equal to 63X minus 65X. 63X minus 65X. Minus 150. Minus 150 equal to 63X minus 65X will give us minus 2X. From here, we're going to divide both sides by the coefficient of the unknown. That is by what is multiplying what we are looking for. We are looking for X, so we shall divide both sides by minus 2, because minus 2 is multiplying X. That gives us minus 150 divided by minus 2. The negative signs we cancel out, okay? Then we now have 150 divided by 2, which will give us 75%. So you see, we've gotten the value of X. X, which represents the percentage abundance or relative abundance of copper 63, is equal to 75%. So we've been able to get the relative abundance of one of the isotopes. Let us now proceed and obtain the relative abundance of the second isotope, that is copper 65. Will be equal to, take a look, 100 minus X, is that not so? Remember, the relative abundance of copper 63 and that of copper 65 would give us 100. So if I know that of copper 63, that of copper 65 is going to be 100 minus that of copper 63. So 100 minus 75%, that's what you get. And this is going to be equal to 25%. Answer, 25%. Good. So we've been able to get the relative abundance of the two isotopes of copper given in this question. And we are done with the first part of the question. Let's move on to the second part of the question, II. The second part, we are to determine the ratio of the isotopes, copper 65 and that of copper 63. This is going to give us 25 divided by 75. So 25 divided by 75. If you work this out, 25 can divide 25, you get 1. So that's 1 over. 25 can divide 75, you get 3. So this is 1 over 3. Okay, 1 over 3. And this ratio will give us 1:3, or 1:3. Remember, that of the numerator is copper 65. So ratio of copper 65, therefore, ratio of copper 65 is equal to 1. Okay, it's equal to 1. That one with 25%. And then ratio of copper 63 is equal to 3. That's how we are done solving this problem. So you say it is a simple one. Is that okay? It's a simple one. All you need to do, in a case where you don't know the percentage abundance of anyone, you assume one of them to be an unknown. Like I took that of copper 63 to be equal to x. Therefore, the order will be 100 minus x.